I mean, one cool thing about these is we do have quite a bit of like operating experience with really high temperature gas cooled reactors. The US built Peach Bottom. This was a 40 megawatt electric actual demonstration. It was like a commercial reactor. And that worked really well. And they're like, okay, this is good. It had 88% availability, 74% capacity factor. It was great. It ran for, 1,300 full power days. Could load follow at 3% per minute. Made superheated steam. That's another benefit. And it just happened to be across the street from big gigawatt scale BWRs. There was this unbelievable economy of scale that gave the BWRs a huge economic advantage. And so it just looked to the people running the plant. They were like, why are we running this dinky little plant when we have these like two big BWRs that are just blowing it out of the water economically? And so they just decided, forget it, let's just shut it down.
A warm welcome back to Decouple. Today I'm joined by fan favorite Nick Touran for a deep dive on the high temperature gas reactor. Nick, I don't think you need an introduction at this point, so let's just get to the meat and potatoes. But first off, welcome.
Thank you. Happy to be here as always. Thanks for having me.
And this is turning into a little bit of a series. We covered molten salt reactors with yourself. We did boiling water reactors with James Krallenstein. Maybe we're going to kind of work our way through, the variety of reactor types. Molten salt reactors, soak up an inordinate amount of attention. And so that episode did quite well. But I think high temperature gas reactors are a really interesting technology to try and get your head around. Very distinct, very different, their own special snowflake, and definitely probably getting the most funding and attention right now in terms of advanced reactors with Amazon's deal with X Energy, where it's not just a power purchase agreement, but actual investment, I think of around $500 million in the company. A partnership with Dow Chemical around deploying their reactors at the Seadrift facility. So I think it's time that we really take a look at this technology and understand it better.
Yeah, sounds great.
And who better than with the nuclear historian, Nick Touran, especially since this is such a historical reactor. 1942, I think, was when it was first theorized. But I'm jumping ahead. I'm stealing your thunder, Nick. Tell us a little bit about the high temperature gas reactor. What is it, first of all?
Yeah, sure. So it's as we've said in the previous ones, you can make a nuclear reactor with any combination of fuels and coolants and structural materials and so on. So gas-cooled reactor is just one that's cooled with a gas. You circulate a flowing gas past the fuel as it's making its heat, and then the heat goes into the gas, heats it up, and goes off and to do something that you're trying to do. And that may be to spin a turbine to make electricity. It may be to spin a propeller for marine propulsion. It could be industrial process heat, all sorts of things. And so it's usually pretty high temperature, high pressure gas. Helium is now kind of the favorite. We have run reactors with the CO2. We've run reactors with air. We've run nitrogen-cooled reactors and a couple other gases as well. So, but by and large nowadays, like people are pretty excited about most of the new ongoing SMR type high temperature gas reactors use helium as the coolant. So there's various. So that's a basic description, and I can talk about why people might be interested in that.
Well, we'll deep dive each of these factors, but. What's the moderator? Is the moderator always a certain thing? Is it graphite?
It's not always, again, many different options. It's usually graphite. It's almost always graphite in the current reactors that people are talking about today. However, it has been, like in previous operating HTGRs, it's been like water in the ML1, which is a nitrogen gas cooled reactor, that truck mounted one that we talked about before in Idaho, that had like a pool of water, like a calandria for moderator, and then it had high pressure nitrogen going through it. You can use beryllium or beryllium oxide as the moderator. That was discussed in some of the early experiments that were run. Used that, and like Farrington Daniels, which we'll talk about, his reactor, he thought maybe beryllium would be a good moderator. You can also run gas-cooled reactors without a moderator at all. And so like in the Gen 4 International Forum, where they listed out back in 2001, they listed out 6 different reactor types. The high temperature gas-cooled reactor was one. That's a graphite moderated version. And then there was also a gas-cooled fast reactor, which is just gas-cooled with no moderator whatsoever. So those are all the options.
Okay. And I guess in our holy triumvirate of the coolant, the moderator, and the fuel, What are we talking about in terms of fuel?
Yeah, these days, and even historically, like this TRISO fuel that you've heard so much about, the tri-structural isotropic, the little tiny pebbles of fuel that are packed into either cylinders or bigger pebbles of fuel are famous. They were developed as part of the gas-cooled reactor program, actually in the UK for the Dragon reactor project, and are still the favorite today. And a lot of the reactor companies that are out there today are saying, like, it's that fuel, that super robust, super high temperature fuel that gives us most of the capabilities that we're interested in. And the reason it's that, I mean, if you're going to very high temperature, you need a fuel that doesn't melt or lose its strength at high temperature. And so you really can't have like a metal in there. And so you go to these fully ceramic, very high temperature fuels. And TRISO is sort of the cutting edge of a long period of development. We went from BISO to TRISO. There's even quadriso. Who knows? There might be like pentiso or whatever, quintiso. Anyway, but TRISO is definitely the fuel of choice at this point for the graphite moderated high temperature gas reactor. The gas cooled fast reactors, which are less commonly talked about and are nearly as well developed, may use different types of fuel, like a nitrate fuel.
So, because you're the nuclear historian, you have tons of knowledge of all those sort of esoteric reactor designs. But for sake of simplicity today, let's kind of contain our conversation, if you will, to helium as the coolant, graphite as the moderator, TRISO as the fuel. And just briefly, again, so that we're clear about what we're talking about, there have been other gas reactors. I guess these would be moderate temperature, lower temperature gas reactors that saw pretty wide scale deployment, mostly in the UK, but also in France. So just briefly, how are those different than what we are going to be talking about today?
Yeah, those would be low temperature gas cooled reactors. So they used like a more typical fuel, originally natural uranium fuel in aluminum sheathed cladding. And you can't go above the aluminum temperature, really. And those were originally made for like plutonium production in World War II. And then so like Calder Hall, Windscale in the UK used air and then later CO2 coolant. That like the air kind of led to a big fire and so on. So there's an early history of those. And then, yeah, France had a indigenous fleet that was talked about before of these UNGG, natural uranium CO2 cooled graphite moderated reactors that they then were they were developing them for power production, but they threw them away and brought in foreign pressurized water reactor technology and built the fleet of that instead. So those are kind of like dead or outdated types of gas-cooled reactors, whereas the high temperature are still very much of interest.
Okay, so let's deep dive this then. We've heard the name Farrington Daniels ponied about. Is that our stepping off point?
Yeah, for sure. So let's see. Farrington Daniels was a professor at University of Wisconsin, a chemistry professor, and he kind of originated the idea of the gas-cooled reactor back in the Manhattan Project. And he then, well, the idea, he had been working on chemical processes that used like a fluidized bed of like pebbles. So he was already doing like pebble bed stuff, non-nuclear. And then he thought, geez, we could do pebble bed nuclear stuff while we're at it. And like, why don't we just take a gas and pump it through there and go straight into a gas turbine without having any heat exchangers or anything. This would be so simple. It would be so, economical, and you could get the high temperatures and all this kind of thing. So he really was a champion of that reactor concept. And they had already been designing and developing gas turbines at the time. And he thought, even back in the 50s or the 40s, that it was like reasonable to make a helium gas turbine right away. Now, that turns out that may have been true, and people have made helium gas turbines, but they are somewhat challenging. There's like leak issues and balancing issues and so on. But anyway, he pushed that, and after the Manhattan Project, he had a team working on it at Oak Ridge as part of the Oak Ridge School of Reactor Technology, or SORT, which is where Rickover went to learn about reactors. And so I think we talked about this on the Rickover episode. Basically, Rickover showed up and was put on a team that was like, let's build a gas-cooled pebble bed high-temperature reactor that directly drives a helium gas turbine and does power production. Rickover very quickly, and the rest of the team really didn't like this reactor concept. It was not popular amongst the reactor designers. Like the young guys didn't like it. it had problems. Like they did the economics analysis of it, and they found out that just the fuel cost alone was going to be like 8 times the current cost of coal. And so they thought there's just no way, even if we make this reactor perfect, just the fuel cost is going to be too high to ever be sort of making commercial type power. So it was not a popular reactor at the time. That the assumptions they were making were probably wrong. Like Weinberg came back, Alvin Weinberg was involved in this as well. And he came back later and said, well, we were a little bit wrong about uranium price. Like there was way more uranium. We've talked about this before as well. Like the uranium price went significantly down from what they were talking about then. But there were other issues. Like Rickover was more concerned about like, how do you seal this thing up? How do you keep it compact? Like it just wasn't very conducive to a submarine, which is what he was obviously interested in. So he sort of commandeered that group and directed them to Weinberg's pressurized water reactor, and that went off, and made Nautilus out of that. And so the Farrington Daniels reactor like shut down for a long time. But then he came back. Farrington Daniels, 10 years later in 1956, published this great nucleonics article, nucleonics being sort of the trade magazine of the time. There's a bunch of them from the 50s now available online on archive.org. And so you can like go read this article. And he basically comes in, he's like, no, now is the time. Like, it was a little premature 10 years ago, but now in the modern age, like, it's much more practical to build this, 5 megawatt electric gas-cooled reactor with helium and so on. So it was like 10% enriched. It had 60,000 cubic feet of concrete, stainless steel liner. It was a breeder reactor. So to deal with the like fuel cycle costs, he's like, well, let's just make it a thorium breeder reactor. And that has carried on. We far later, we did see like thorium breeder gas-cooled reactors that we'll talk about. So this was like, he published a lot about this and it got a lot of hype, and it actually inspired the creation of the first actual high-temperature gas-cooled reactor, which was in the UK. It was the Dragon project, and it was directly inspired by like this Farrington Daniels article in Nucleonics. And it was this huge like, we'll get into it, but it was like a huge collaboration between all of Europe. It was like the European reactor development program for this Dragon thing. So anyway, that's the really early history in the Farrington Daniels. Daniels himself sort of gave up in nuclear and went off and did a lot of interesting work on like solar power after that. But he really was the intellectual father or grandfather of the gas-cooled reactor for sure.
We're gonna walk through this history. It strikes me that there's a number of stages. We have Papa Farrington theorizing this. We have early work at Dragon, and then there's sort of two main sort of research areas or deployment areas. One in the U.S. With Peach Bottom and Fort St. Vrain, and one in Germany with I love German, like how you can just string together endless sounds and words within one word. But the Arbeit Gemeinterschmascher, I'm messing it up. But the AVR,
the AVR,
yeah. My German listeners know I'm full of shit when I string those words together. And this thorium THTR. So that seems like sort of a way to kind of organize things in terms of development. We had the South Africans sort of jumping on board at a certain point, and now China is, as all things nuclear, seems to be at the cutting edge, not of making PowerPoints, but of pouring concrete and building reactors.
Building big reactors, yes.
Big uns. So wherever you want to take it, but I just wanted to kind of lay out that very gruff grounding of sort of where things are happening and when.
It may make sense to talk a little bit about like some of the other reasons people are interested in this type of reactor, and then go back into the history just to kind of back and forth it a little bit. So
love it.
So why do you want to go to high temperature? There's a couple reasons you want to go up to like higher temperature, and those reasons include like one, just the laws of thermodynamics say that if you have high temperature heat, you can convert a higher fraction of that heat into electricity or some other usable power than you could with lower grade, lower temperature heat. So that's thermal efficiency. And if you can get nice high temperatures, you can get nice high thermal efficiencies. And if you can get more electricity for the same amount of heat, then that should help with economics. So there's an economic idea that going to high temperature is going to help you just extract more of what you want out of a given amount of natural resources. So that's one major driving force. Another major driving force is the potential compatibility with, instead of making steam and running it through a steam turbine, is using an actual gas Brayton power conversion cycle. And I mean, gas turbines are much smaller than steam turbines. They are much more flexible. They can kind of ramp up and down regularly easier. And perhaps essentially, one of the really early drivers of gas reactors was for marine propulsion, like running cargo ships on a nuclear reactor. A Brayton cycle turbine maintains its high efficiency at any power fraction. So if you go down to like 10% power, 50% power, 100% power, it has the same, roughly the same efficiency. And so that's very important if you're either deeply load following, or if you're a marine, if you're a ship, you want to be running at very low power when you're cruising around slowly, and you want to be running at full tilt out there. But in all those cases, you want to be economical. And so having the ability to do that with a kind of small, compact turbine that can ramp up and down without losing efficiency is very interesting. And so that was a big driver for like why people wanted this. Today, a major driver is the industrial process heat. So using nuclear derived heat to do some kind of industrial process. And there's all sorts of industrial processes that need high temperature heat that only, a high temperature reactor can really get to easily. So these are things like refining oil, or extracting tar sands, or steam reforming methane, or making hydrogen, or many other things. There's certain types of desalination that can work better at high temperature and so on. So and that's really driving, like the X Energy project is, their primary partner is Dow Chemical, who has all sorts of industrial facilities that need heat and they need electricity. And if they can get both from a nuclear source, then, that's great. That helps them phase out use of fossil and so on. So I think those are, and then I guess lastly, there's a safety benefit. Like if you have like fully ceramic high temperature materials, and you're using crazy robust TRISO fuel, then you get to a point where like there aren't really any credible scenarios where you can go above the melting temperature of this fuel. So there really isn't a meltdown scenario for this type of fuel because it's just so strong. There is a fission products leak out scenario. So like once you get at a certain temperature, the volatile fission products just kind of come pouring through the structures. And you can break a TRISO pebble or fuel pin or whatever, but the retention of fission products and the various like sort of worst case scenarios are a lot less scary than they are in some types of reactors. So there are some safety benefits of going to these super robust high temperature materials. So that's kind of, I think that covers most of the driving force. Yeah, people were like, it's going to be cheap. It's safe and it works for like many more applications. So that's I think enough to sort of motivate additional work into it.
So you mentioned this idea of using the Brayton cycle, which is, again, the expansion of hot gases through a turbine, if I'm understanding correctly, bypassing
it's like a jet engine, basically, yeah.
This whole need for a heat exchanger and a steam loop. You can't boil air and send it through a turbine like you can with a boiling water reactor. So in any case, from what I understand, there's not really been any successful, or none of the deployments I talked about earlier in terms of Peach Bottom, Fort St. Vrain, AVR, THTR. None of them went to a Brayton cycle. Is there a reason for that?
Yeah, I mean, the only Brayton cycle nuclear reactor ever run that I'm aware of is ML1, the little truck-mounted guy. And so I think there's some others in development now, but that's the only one that actually did it with like a nitrogen turbine. There are challenges. It's nice to have a heat exchange because, like, especially in the early days, like one of the purposes of this first experiment, Dragon, was to find out like how contaminated would the helium get. So like how much of the fission products would be pouring out of the fuel, getting into the helium stream, and then going off to wherever your power conversion is. And they didn't know that it would be good or bad, or they didn't know anything about it at first. And so they had to put in a heat exchanger and and have the heat dump on the other side of that just to measure, to see if it would even be practical to do a direct cycle. And so and then as they sort of operated, people found, well, some stuff does leak out. There are things that break. There is some contamination. Tritium comes out. Tritium's generated, it's actually a fission product. It's a ternary fission product, and you can get it through other means as well, like from impurities and so on. So like, tritium comes into there, and then just different like accident scenarios can be challenging. Oh, and like a helium gas turbine, which again, people have built like a handful of these. There's a great German publication that Rod Adams pointed me to that has like all the operational experience of the like three helium turbines. And yeah, they like leak. They had to adjust when you have the heat going through, like keeping the helium in under like different thermal gradients within the turbine is very hard. So like things leak, turbo machinery leaks, and so leaking potentially contaminated helium is just a little bit too scary. I think people still want to get there, and there's still certainly reason to get there, but just going to doing heat exchange to steam has been what people have done so far. It's kind of the like easy-ish first step way to get going, so we can get more experience and then maybe eventually switch back over to a gas turbine. I think like pretty much every reactor concept in this space starts out as either a direct or even indirect cycle to a gas Brayton cycle. Like there might be a helium to helium heat exchange that still drives a gas turbine, but then inevitably like 5 or 10 years later, they drop the helium turbine to the Brayton cycle turbine. They put in a steam cycle, just again, probably to like be able to focus on one thing at a time, which I think probably makes sense. But yeah, the Brayton cycle's still out there as a dream.
So I think we'll get into like the challenges of kind of the leakiness of helium, but just in terms of like I'm thinking probably on the opposite spectrum of running a gas or maybe even a supercritical gas like CO2, which is being looked at now, that's a very kind of dense fluid where you can get a very compact turbine. Helium, second lightest element on the periodic table. How does it perform in terms of just that kind of volumetric density and its ability to sort of be circulated and create power on its own without going through a heat exchanger?
So helium is a pretty good heat transfer fluid, and I mean it's usually pressurized to like hundreds of psi or 4 or 5 megapascals. It's very high pressure gas, and it is like a pretty good heat transfer gas. It's a lot better than most of the other gases. Like something about being a small gas makes it easier to like pick up heat and transfer heat. So it's like not a terrible heat transfer material on its own. I think the big challenge with it comes in like when you're doing accident analysis and you have to worry about like a depressurization accident. The thing about high pressure gas is that if there's like a hole, it all disappears. Like it all just poof, it's a depressurization accident. And so all the gas, all the coolant immediately leaves the room, and you're not in a vacuum. You have like regular ambient pressure air at that point. So, but the big constraint on these is the decay heat afterglow cooling in a depressurization accident. So even if you can pump lots of heat with helium, no problem, but it's that decay heat scenario that like limits the design. And that's one of the reasons that these gas-cooled reactors have literally like 1/10 the power per volume than like a light water reactor. Graphite itself can absorb a lot of heat, has a high heat capacity, and it's also a good heat conductor. So the scenario is like when that helium goes away, no problem, everything heats up a little bit, and it's just conducted out to the vessel walls. And these reactors are always very tall and very skinny, and that aspect ratio is so that heat can easily conduct out to the outside of that wall, which is then cooled through some either active in many sort of older designs or passive means in most of the ones being worked today. It's kind of more in the Gen 4 philosophy to like not require an active safety system. So you can have like naturally circulating air with a chimney or something on the outside of that vessel that picks up that decay heat and carries it away in that kind of an accident. So, but yeah, it's astounding. The power density is probably like maybe one of the most obvious downsides is that these things are big. When you're 10 times the size of a PWR, for that reason, and plus there's another reason for that, which is neutronics, which is that the neutrons, when they hit graphite, they take a lot more space, a lot more distance to slow down to a thermal neutron, and so you need much more moderator in there, where you just need like a little tiny thing of water around a fuel pin, so you can have these very compact cores. That's why Rickover went with the pressurized water reactor, because you could put a little tiny core with very high power density in a little submarine. Well, with graphite, it's 10 times bigger for neutronics reasons and for the decay heat removal reason. So it just doesn't, and that doesn't kill you. Like, you can have a big reactor, that's fine, or you can have a very low power reactor, that's also fine, but it's certainly not the most compact reactor out there.
So I'm not sure which way you want to take it. I mean, that leads me into all sorts of questions about, okay, so what does containment look like? Does this mean your civils are very large? We could go there, or we could sort of jump back and do some history lessons and kind of go back and forth between history and technical. I'll leave it up to you.
Yeah, let's talk about a few that we ran just a little bit, just so we can see. I mean, one cool thing about these is we do have quite a bit of like operating experience with really high temperature gas cooled reactors. And I'll just kind of hit a few of them briefly. So like Dragon was this thing started in 1959, the big European collab. It was designed to be a thorium U-233 breeder, as a lot of the early ones were. 20 megawatts thermal. It was in Winfrith, the UK. It's basically like the UK's version of the National Reactor Testing Station. They did a few things out there. And that's where they did establish the use of this coated particle, the TRISO fuel thing. I think most of your listeners probably know about. It's like UO2, little tiny, sub-millimeter diameter, surrounded by low-density carbon, which is where some of the fission gases end up, and then a layer of high-density carbon, and then like silicon carbide, and another layer of carbon on the outside of that to prevent them sticking during the manufacturing process. They had a goal of like, let's see if we can get the helium leak rate down to 0.1% per day, and they were able to get there. They worked on the helium purification system. There's a lot of things that can get into that helium. Like from the outside, you may have like moisture or air coming in. From the inside, your graphite may be like off-gassing moisture, or carbon monoxide from neutron irradiation and CO2 and other things. You have to clean all those out of there. They did find kind of the regular operational experience type things. They found stress corrosion cracking from hydrogen chloride. It was supposed to just be a 5-year project. They did get like 6 extensions, but eventually they closed it out. Like basically, the UK was building another reactor on that site, the steam generating heavy water reactor. So kind of a fancy can-do, so to speak. And at this time, mid 70s, they couldn't find anyone interested in like developing this reactor further. There wasn't an industrial partner or an industrial interest. And so they just closed out the project. And like, projects are supposed to, I think the definition of project is it has a start and an end. And so like, yeah, they learned a lot. They formed the baseline of the technology, and they closed it down because there was just no one commercially interested in it at that time. So let's see, another early one. Yeah, the US built Peach Bottom, this was online in 1967. They contracted it in 59. It came online in 67. And then it was shut down like 7 years later, 1974. Really great papers on its history and so on. They learned all sorts of cool things. This was a 40 megawatt electric actual demonstration. It was like a commercial reactor. It tried out different types of fuel. It did this BISO type fuel that I was talking about, but it didn't retain enough fission products. It was like blowing fission products out the pebbles. So they did add that third layer to like really that's where they added this, the silicon carbide structural layer is where you really start containing the fission products. And that worked really well. And they're like, okay, this is good. It had 37% thermal efficiency, up from like 32 or 33 in a light water reactor. Made superheated steam. That's another benefit we didn't talk about earlier, is like a light water reactor makes saturated steam. And so you have these like custom turbines that are like very nuclear specific, and just the steam turbines, whereas if you can make superheated steam like a fossil plant, then you can use total commodity off the shelf turbines, which are, for your steam cycles, are even cheaper. But that thing operated well. It had a 88% availability, 74% capacity factor. It was great. It ran for, 1,300 full power days. Could load follow at 3% per minute all the way down to 30%. It was great. But yeah, it was like pretty small. It was, 40 megawatts electric. And it just happened to be across the street from Peach Bottom's Unit 2 and 3, which are big gigawatt scale BWRs. And basically, at this time, the BWRs were operating fine. Peach Bottom was operating fine, but there was this unbelievable economy of scale that gave the BWRs a huge economic advantage. And so it just looked to the people running the plant, they were like, why are we running this dinky little plant when we have these like two big VWRs that are just blowing it out of the water economically. And so they just decided, forget it, let's just shut it down. There's really no point in like bothering with this thing. So that's probably like one of the better operated gas cooled reactors, but it just couldn't compete with the big BWRs, and so that one got shut down in the U.S.
I mean, that's an extraordinary availability for what this was basically the first high temperature gas reactor really built in the U.S. certainly at a commercial scale.
Yeah, they had a few little guys out at Idaho, but yeah, I think it did great. That's like way higher than you would sort of expect. So totally. I think they really did a good job. And there's cool little pamphlets I've got off eBay, summarizing it with cool pictures and stuff.
And just thematically, the two U.S. high temperature gas reactors, the two commercial ones, were prismatic, meaning not these. I call them. Everyone laughs at me, but the gumball machine reactors are the pebble bed ones. In Germany, and now X Energy's reactor, these were prismatic, meaning geometric, like hexagonal bits of fuel element.
Yeah, they have like a big chair-sized hexagon of graphite that has like dowel rods on it that you can, and they kind of stack up on top of each other, and they have coolant holes drilled in them, and they have fuel holes drilled in them, and you drop in basically fuel pins, but they're fuel pins with a bunch of little TRISO particles embedded in the fuel pin instead of like a slug of uranium oxide.
So what about Fort St. Vrain? This didn't go quite so well as Peach Bottom. It's sort of the laggard.
Yeah, so then we built in the U.S. Fort St. Vrain, which was a 330 megawatt, big boy. I guess that's still called an SMR, but that's like ridiculous. It's a very large helium cooled design, also prismatic. It had basically a terrible operating experience. It had all sorts of problems. It shut down all the time. And there's like a real sad article I just saw from 1988 that Matt Wald wrote that says the headline, it was like, world's safest reactor shutting down because it never runs or something like that. And that's basically what happened. I mean, it was a good concept, good design, but like the practicality and the operability of it was bad. They did learn some lessons. Like it's not that these reactors are inherently bad. They like learned a few things about like what not to do. But yeah, this thing was big. It was in a pre-stressed concrete reactor vessel. So like this vessel was 10-meter diameter. The walls were like 3 to 5 meters thick of concrete. Whoa. So it was a big boy. And it was 23 meters tall, so like 75 feet tall for this like huge concrete vessel. It had like everything in that. It wasn't just the core. It was the core. It was the steam generators and the helium circulators were all within this giant pre-stressed concrete vessel. Again, helium cooled, almost 5 megapascals. But yeah, they one of the things you can have in a gas-cooled reactor is like if there's like a leak in the steam generator that shoots water into the helium thing, and now you have what's called a water ingress. So you're shooting water in, water is going everywhere. It's all at high temperature. You can imagine what like high temperature water does. It oxidizes graphite, it causes corrosion, it causes things to get sticky and break. And man, there's some crazy stories where like, they have moisture sensors in the reactor, and like for whatever reason, the operators thought at one point that the moisture sensors were like spuriously activating. They're like, those stupid moisture sensors are going off, and they sent someone down to like take it off to fix it or just unhook it. And when they like unhooked it, like water came pouring out. It's just like not supposed to be in there. And so yeah, they had like very long, prolonged outages for all sorts of problems. They also, I think a lot of the actually water ingress problems were from the helium pump or the helium circulator had, it's got moving surfaces. It has water lubricated bearings, and those bearings with the water in them kept like leaking water into the system. And that was kind of like the main issue. And so one of the big lessons learned from Fort St. Vrain is like, don't use a water-cooled helium circulator. Like if they had just not done that, that probably would have gotten rid of maybe like 80% of the problems that they had at that reactor. So it's like a huge design flaw. And they like noticed it early. They were like, maybe we should change out that cooling on that circulator. And they're like, nah, don't worry about it. And like it ended up just biting them again and again and again. They were like, they'd change power, and like ice would be condensing on the instruments and control rods were getting stuck. Yeah, ice formed on the chillers for the gas cleaning system. Control rods rusted, and so like rapid shutdown, they were like, insert the rods, and like the rods didn't go in, or they went in really slowly because they were just like rusted up and messed up from all the moisture they got in. So like, there's a I found like a newscast video. I'm looking for old videos, and I found one that was like they evacuated the plant because they thought they blew a primary tube, but actually it was again, it was the helium circulator bearing. It dumped like 113 pounds of helium out and so on. They just had like all sorts of problems. And so, yeah, overall, it had a 14% capacity factor. They had 520 people working there, and like it was just too expensive. And so it got shut down.
Okay, so mixing in the kind of history with the technical, so we don't get monotonous on either. Yeah, what stands out for me is this pre-stressed concrete containment, which just sounds like the most insane overbuild. You said like 3 meters thick.
Yeah, 3 to 5 meters.
And again, pre-stressed, which would, to my uneducated ear, sounds like that's to deal with big pressure transients. Now, in a high temperature gas reactor, you don't have the potential for hydrogen explosions from I guess it's like the zirconium water reaction at high temperatures. You make hydrogen. You don't have steam explosions. So pressure is not your enemy here. But it sounds like helium is a real challenge to keep inside. So let's just chat briefly then about high temperature gas reactor containments and kind of what's different from pressurized water reactors, if it's hunky-dory easy or if there's just new different challenges.
Yeah, I mean, it's definitely different. Like they basically say, I mean, the pressure in a high temperature gas reactor is the normal nominal pressure of the helium. Like that's the high pressure system. There isn't like you're right, there isn't like a big pressure surge or anything that anyone's anticipating. It's just like you're running with like very high temperature, high pressure helium gas. And so, yeah, it's very robust, obviously. It's very strong. It does all the shielding for you, but like a lot of the designs that we're seeing now aren't actually using this concept anymore, the pre-stressed concrete reactor vessel, because like decay heat removal through 5 feet of concrete is to do passively is hard. And so the reactors that had these huge vessels generally had an active safety system, because when, you have to, not a very complicated one. It's like they were like the fire water cool down system where you basically you hook a fire hose up and it cools. There's a little steel liner right inside. So it goes like reactor and then steel liner, 3/4 inch thick steel, and then the 5 meters of concrete. And so that steel needed cooling, so they had like cooling channels in there. So anyway, the active decay heat is like, okay, you've got you've lost all power. Well, let's let's hook a fire hose up and cool that thing. And that's the plan there. But that, again, it like doesn't fully meet the like fully passive Gen 4 objectives. And so a lot of the reactor designs we're seeing now are kind of going away from, as far as I can tell, they're going away from that big super mega concrete vessel and going to just lower power densities that you can straight up conduct out and then do this natural circulation along the outside thing. So, but yeah, it's cool because, I mean, you build that huge concrete thing. Yeah, that's expensive. But then you don't really need like a very strong building. You want to have the building maybe be airtight so that if helium gas leaks out, you can still run it through a filter, but it doesn't have to be like a big, strong, you don't have this huge containment dome over the top of it. Now that huge containment dome helps for like aircraft impact. And so I guess I'm not 100% sure like how you do aircraft impact. I mean, I think with the pre-stressed reactor vessel, it probably can just like handle it to a degree, but I don't know. I haven't actually seen the analysis on that. So where it ends up for that sort of more modern post 9/11 type of thing, I'm a little bit unclear on.
So one big thing is, you still need a biologic shield around these reactors. They're still putting out a ton of radiation. So you think, okay, well, maybe if you don't need to contain all that pressure, you don't need thick concrete walls. But it sounds like you still do because you got to deal with a biologic shield. Is that correct?
Yeah. You definitely still need, the standard 8 to 12 feet or whatever of concrete or some other or equivalent biological shielding one way or the other if you're going to have anyone doing the operations anywhere nearby, or if you have any like equipment needs to be radiation shielded as well. Like if you have any electronics or whatever, like, yeah. So yes, you certainly need the normal amount of radiation shielding. In fact, You might need a little more than in some reactors because, like, I mean, again, if you're not using that giant 5-meter wall, if you use the 5-meter wall of concrete for your vessel, you're good to go. Yeah. But if you don't, like, yeah, you can't really put as much internal shielding as you might in another type of reactor because, again, you're relying on this conduction of heat from the core to the outside of the vessel in order to do passive decay heat removal. And so if you put too much shielding inside that, you may not be able to get heat through it because radiation shielding maybe is also a thermal conductor or a thermal insulator. So you probably need, if you're going to do that kind of thing, you may have like a cooling path and then a bunch of biological shielding on the outside of that. And that's sort of a typical design.
And I guess one last thing, you're not dealing with pressure, but you're dealing with a really leaky coolant.
Yeah.
So any perforations need to be very, very carefully made and
yeah, the sealing for these things, I mean, helium goes through, it can get out any little tiny leak. And so a lot of the like welds on these are like double sealed welded where they have like one weld and like a second weld downstream from it. And yeah, all these, the tolerances have to be like way more tight than a typical tolerance for vessels and seals and valves and stuff like that. Any moving parts, like just again, because the helium leak rate out of any tiny little crack or hole is going to be pretty high. And like, helium, you know, there's been concern there isn't enough helium in the world. At this point, like helium isn't the craziest expensive thing. You're not expected to be consuming too much of it. But if you're leaking a lot of it, like, yeah, you may be leaking the valuable helium, but also like any like slightly radioactive things in there. So that is a big challenge in these machines as well. And you have to, like, if you're anything that, like if you're putting fuel in, well, you got to have like some kind of system that sort of like allows you to bring fuel from the outside and like puts it in there and then gets it into this high pressure system without leaking too much. So
it's interesting. I just got back from the Canadian Nuclear Association conference and they were talking about the success of our refurbishments. Again, these are the engine swap outs essentially of almost the entire nuclear steam supply system of our CANDU plants, which involves, you know, taking 480 fuel channels out, 960 feeders that sort of go into each end of each fuel channel. There's a shit ton of welding that needs to happen. And they were talking about the sort of weld failure rates at the very beginning of these refurbs. And it was something like 10 to 15%. And they've gotten down to less than 1% due to this positive learning curve amongst the welding workforce. And that's definitely something that, you know, took a few years to get dialed in. It took really careful planning. You know, these life-size mock-ups that we have at both the Darlington and Bruce site where workers go in and practice in a non-radioactive environment and you know, do all their tooling. But suffice it to say, I think like just to go on a slight rant here, like there's this sort of hubris of the now that we live in where we're like, well, we have, you know, AI and we have incredible computation. And so whatever they did in the 80s, we can do that easily. But you know, I think we got into this a little bit in the episode on the machines and machining tools with Noah Redberg, but this idea of sort of craft labor, of esoteric knowledge that is transmitted from person to person or accumulated over a lifetime. Like it takes a while to dial in these skills and the need for welds that are, you know, even more exacting than your average, you know, nuclear level weld on a pressurized water reactor does seem to be not a showstopper, but like a major challenge and one that's overlooked in the era of, you know, nice PowerPoints and learn to code and send your best and brightest off to Wall Street to financialize the economy. Rant over.
Yeah, I mean, I agree. And these things can't be learned by reading a book or thinking about it or whatever. And so, I mean, this is one thing I am encouraged by the fact that we are seeing, you know, a lot of the companies out there are now saying like, we don't care about PowerPoints. Like we're just building. And like, I appreciate that to a degree because a lot of the stuff you're talking about, just like the basics of plumbing and controlling and heating up any fluid. This may be molten salt, it may be liquid metal, it may be any helium gas. And there's relevant stories along these lines of like, it's hard to deal with these. These are specialized materials. And the only way you're ever going to get good at them is to get hands-on with them. And so we are seeing, you know, these microreactor companies and others are now saying like, we're just building a loop like with our stuff in it right now. Like we don't care if our design is, you know, 0% complete. Like we just want to start building up hands-on experience with the coolant. And I think that is really valuable. And, you know, there should be a way that we can, ideally we'd have like a national program. I'd love it like INL if they had like a, I've said this many times, but like one of each type of reactor, kind of small, or you can go in there for 6 months and work on it and get hands-on and do training on it and learn the ins and outs of like that particular coolant. And that would be like a great feeder for like this. If we really want to expand nuclear, we need to get hands-on training for fairly exotic types of machines and coolants and flows and instruments and all that kind of thing. So yeah, it's a real problem. You can't just walk out and know how to work with helium or any of these things. And so just getting more people working on real loops, real reactors, even if they're small and sort of uneconomical, that still could be valuable.
So where do you want to take it from here? Do you want to leap over to Germany? Is it worth going through those reactors? I guess we've just talked prismatic, so there's probably some lessons, and we should describe the pebble bed reactor beyond my gumball machine description.
Sure. Yeah, let's talk briefly about the two German ones. They're cool. So you already mentioned AVR. I didn't even write down what it stood for, so thanks for knowing that.
Oh, I couldn't ring it off. Even I don't really know what it stands for. I just know it's one of my favorite German words.
Great. Well, yeah, so that's a small one. It was 15 megawatts electric. This was, a spin-off out of Dragon. Germany was like, hey, we want to build our own. We like this technology. And so they built it in 1960. It hooked up in 67, shut down in 88. It was basically like the Daniels pile. They were like, let's build the Daniels pile. And it was a consortium of electric companies, kind of similar to like how Yankee Row, the PWR, was built. Like a bunch of utilities came together and were like, let's do it. It had lots of accidents and issues, as sort of expected in the early days of any kind of reactor. It had the nickname Shipwreck, which is kind of a funny nickname for a reactor. But they figured out a lot. They like learned all sorts of stuff. They did have a water ingress accident. They caused a little bit of groundwater contamination. Lots of strontium-90 came out. They broke some pebbles in it. The bottom reflector broke. They're decommissioning it now. It's cost like $1 billion already, expected to be like 2.5 billion more. So like all those, there were a lot of like hot spots and flow instabilities where like there would be a place where the fuel got like so hot that more fission products came pouring out. Again, these pebbles don't break, they don't melt, but they just sort of release all of their fission volatiles. So again, it's a lot better than melting, but it still can release fission products. Interestingly, this reactor, the AVR, was licensed to China and was the basis for the HTR-10, which is how China got into high temperature reactors in the first place. And now we should make sure we have time to talk about what they're doing. They are now, vastly ahead of anybody. They built the HTR-10, which they ran for years, and then they just built the HTR PM, and then they built two of them, and now they're building like 2 12-packs of HTGRs, which are like under construction. You can see the pictures of like, 50 cranes and 2 big structures, each with 6 different HTGRs.
Looks like a revolver.
It looks like a revolver, like each cylinder is a reactor, and it has shared, the fuel handling equipment is like, it rotates around and services all 6 of them. It's actually quite impressive. And so they're now, by far the world leaders in gas-cooled reactors and that kind of came out of this AVR. So sorry, back to Germany. Anyway, this may just be Germany. That's why the decommissioning is so expensive. Like there's a report in 2014 with, stories about how they disabled safety systems and, they're kind of like whooping the people who ran it. I don't know like how serious it actually was or how much of it is just like Germany hates nuclear. But then, based on that, they did go and build a 300 megawatt TRISO pebble bed reactor called the thorium high temperature reactor, the THTR, and that was sort of a big Fort St. Vrain size thing. Similar size, had a 5-meter thick pre-stressed concrete vessel. It was 25 meters in diameter. This one was like fat and a lot less tall. Fort St. Vrain was like skinnier and much, much taller, twice as tall. They did have, because it was so fat, they had like control rods in the vessel, and they would like go down and just like push into the pebble bed. And a few times they just like smashed pebbles with their control rods and broke them and like caused all these like broken pebbles that then when they got down to the bottom, they jammed the fuel handling machine that was supposed to like suck the pebbles out. And so they had all sorts of troubles with like just OpEx type stuff. They did release some protactinium-233 like right around Chernobyl. Like it never was really noticed because Chernobyl had just happened. It was like literally like a month after Chernobyl. But like later people were like, wait a minute, what's this protactinium signature out here in this forest? And they traced it back to an incident that actually happened at the THGR. But like overall, I mean, yeah, it had its problems. But I don't know. It like, we learned something. It unfortunately, like, yeah, it was critical in 83. It reached full power in 87. It shut down in 89. So kind of another like disastrous like waste in terms of they built it and ran it and then just immediately shut it down. They probably could have got a lot more information out about it. I do like the idea that like you can make these a breeder. Like, so you put in some sort of HALEU pebbles and then you throw in some thorium pebbles, you know, and those are like the breeding pebbles. It's kind of a cool way to do thorium breeding with without having to go all the way to fluid fuel. It's kind of like quasi-fluid fuel with the pebbles. And then, you know, when they come out at the bottom, you scan them and you can be like, oh, that's a thorium one, send it over to reprocessing, or that's a uranium one, send it around for another pass. And that's cool. That's a cool concept. And that does allow you to get the advantages of breeding, get the really long-term sustainable type fuel cycles and stuff. So that's definitely cool.
So that thorium pebble's not TRISO then, because reprocessing TRISO is a nightmare. Is that correct?
I think it is at least partial. It's kind of like TRISO. It basically is TRISO. You can reprocess TRISO chemically. You can dissolve it in acid and you can get it. What I've heard is that like the cost of reprocessing TRISO is like high. You've talked about it before, but like TRISO fabrication is very expensive right now. Maybe it could be cheaper. And so similarly, TRISO reprocessing is also pretty expensive. It's such a robust container. You got to kind of work to get in there and reprocess it. But yeah, and maybe it's BISO or something. I'm not totally sure on that, but.
So scale, like the theme here, at least, you know, we don't have a ton of reactors to build off, but scaling seems to be a challenge. And going up to the 300 megawatts seems to be too high. The Chinese, they started off with a 10 megawatts kind of prototype test reactor, and I believe they're 6-packs. They're not. I think the overall output is something like 600, but each one is about 100 megawatts. X Energy similarly, XE100 is, I believe, around 100 or 80 megawatts like 80. Electric.
Yeah, exactly. So I think, yeah, what people have basically, I mean, I think the world agrees with exactly what you said. They're like, okay, 300 is too big, so let's just do modular. And so that's exactly what's happening. Those HTGR PMs are 100 megawatts electric each. And they're like, well, we'll just put them in that 6-pack. We'll mass produce a bunch of 100 megawatt reactors. We'll slap them into this huge, you know, regular looking nuclear, like a gigawatt scale looking nuclear building that has the revolver slots, one for each of the 6 reactors, and then have, you know, a bunch of shared facilities in there, like shared turbines, for instance, that take the heat from all of them and can do stuff. And I mean, besides just scaling, there's other reasons you might actually want small. If you're doing process heat stuff, then there's a pretty high premium. Like any process heat stuff you're doing costs money, and you're going to lose money if there's downtime. So if you go down for refueling and you got to shut down your industrial process, well, that's a big pain. But if you've got a 6-pack and you can refuel, you know, or if you can do maintenance on one at a time, a lot of these do online refueling, first of all, because you can just drop pebbles in and pull them out every day. But you still have to go down for maintenance and repairs. But if you have a 6-pack, well, that actually works out great because you take one down, you do maintenance on it, but the other 5 are still producing power and able to service whatever industrial process heat thing you're doing. Now, can you take one down if it's in, you know, while the other ones are still operating and do maintenance if they're in kind of close quarters? That's, you know, there may be a high radiation field or something that you have to worry about. So there may be an advantage of spreading them out a little bit farther than what China is currently doing if like uptime for process heat is the primary goal. I'm guessing like China doesn't really care about that as much. They have so much energy demand that they just kind of want to build all types of reactors and see how cheap they can run them, or see how economically they can run them, I should say.
Just, I guess, a couple of things here. I mean, one thing is, you know, in the era of PowerPoint reactors, like the schematics I've seen for the bubblegum machine, like what you see is a reactor pressure vessel and you see, I don't know, like 50 pebbles kind of moving through. But we're talking like 200,000 pebbles, I believe, in the HTGR PM. Like, just as it kind of blew my mind in terms of schematic versus reality, and just hearing that number seemed kind of nuts. But
yeah, no, and we've done the number of pebbles that have been handled in like THTR and others. I mean, it's in the millions. Like they discharge and charge like 1.5 million pebbles in one of those reactors. So we've handled like several million pebbles out of these reactors before. And yeah, the math behind like pebble flow is super interesting. It's like a really complicated complicated field of mathematics called granular flow. This is a side note, but like as an intern in Idaho National Lab many years ago, like my cube mate was this British applied mathematician. He was like the smartest guy I've ever met in my life. Maybe I mentioned him before, but he was specifically studying the flow of pebbles in these pebble bed reactors to see like how far would they move and like what would the burn up gradient be and how many times can you send them over. Really interesting stuff. So, but yeah, there's a ton of pebbles in there, but and again, we have lots of experience handling them, some of which was bad, but we learned like don't smash your pebbles. Like
with the control room.
Yeah, it's one of those like you probably should have known that, but good lesson to keep on the list.
I guess another kind of overall theme that comes up is the lifespan of these reactors. And it sounds like a lot of them, to be fair, were limited more by economics than actual capacity factors. I guess we're not referring to the big boys, the Fort St. Vrain and the THTR, which, it was, particularly bad economics, but also just terrible capacity factors, maybe related to scaling so high. But in terms of lifespan, I don't think we've really talked about heat exchangers yet, but just running at higher temperature stresses metals out. You need more specialized alloys. Some of those are harder to weld. So in terms of lifespan, we're seeing pressurized, water reactors running out into being relicensed to like 80 years, I think. So what are we expecting here? Because that's has a major impact on LCOE.
Yes, at higher temperature, corrosion goes faster. So like I would expect the steam generators to last less long than in a light water reactor. But you can replace the steam generator without replacing the reactor. So like I think, yeah, you'll be replacing steam generators every 20 years or whatever, unless you get some, real nice material advances. But the reactor itself, probably can last 80 years. There isn't, you've got lower density core materials, and so you may have like more neutron leakage that can reach the walls of the vessel and so on, but you're also at 1/10 the power density. So like you're barely, those neutrons are 1/10 as intense as they would be in like a pressurized water reactor in terms of just like the source of the neutron. So I think those things would kind of balance out, and you could expect to get like a nice long life out of a gas-cooled reactor. I think like 60 and 80 years out of one reactor is within reach for sure. And some of these older graphite moderated reactors that were low temperature had problems where the graphite structure got messed up. But at high temperature, it like anneals, like all the damages in the graphite actually mostly anneal out. And they even did like specific annealing steps in the AGRs where they would like just bring it all up to a higher temperature for a while to like shake out all the issues in the lattice. And so at high temperatures, it's just a little bit less of a problem. Like the biggest problems will be like corrosion. Like corrosion is going to be there of, whatever metal is still in there. You're going to have like some corrosion. Control rod structures may have something that can corrode, but again, you guys, in terms of like maybe there's a refurbishment, it probably wouldn't be as big as a can-do refurbishment, but I think they could last a long time.
I guess let's talk a little about process heat, because this is one of the big economic cases for high temperature gas reactors. Obviously, baseload electricity, it's kind of baseload is back, or baseload is the favorite word of the I'm not sure which, maybe she's the Minister of Energy in Sweden. But certainly it's not been well compensated in deregulated markets recently. And so the idea of being able to sell something that's higher value, I think, is one of the use cases and attractive here. But let's talk about some of the challenges of just using nuclear process heat. I think category errors are very frequently made between nuclear and more conventional forms of power generation, because that's what we're familiar with, and you have to fill in a lot of knowledge that's lacking to understand the intricacies and the differences. I wrote a little essay on. It was actually based largely off of our conversation on microreactors, but that microreactors are not batteries. They're not like diesel generators. There's a lot of differences. So let's just briefly touch on process heat and I guess some of the challenges of nuclear versus conventional process heat.
Yeah, as far as I can tell, like the process heat customers would love to have nuclear generated process heat. They would take it if you got it, and they, if you can sell them heat, BTUs at reliably and for a reasonable price, they would happily buy them. But I really don't think they want to operate or own nuclear plants. Like when you talk to like oil companies and be like, hey, so you guys are going to become the operators of this plant. Like that's extremely hard to accept from the oil industry. Like, so I think a lot of like companies are kind of thinking of doing like PPAs, where maybe the nuclear company owns and operates the reactor and sells heat and electricity to some industrial facility that's like off to the side. And yeah, those facilities are not going to buy it if it's expensive. They're using natural gas for heat right now and electricity. It's like super cheap. It's super reliable. It has problems. Like you may want to conserve it for other uses. You may want to worry about climate change or anything like that. But if you can make nuclear heat cheaper and more reliable and easier logistically, in some remote area, then there would be customers for it. But yeah, they just won't tolerate like low reliability stuff. And I think that's our biggest challenge is like, okay, we can build gas cooled reactors, obviously. Can we operate them cheaply and reliably? To be determined. I mean, I think the answer is yeah, there's reason to think we can, but can we do it at scale in an environment where we can just sell it totally reliably to process heat off takers? That's TBD. And I'm happy to see people interested in it. I'm really excited that Dow, is investing in it and seriously considering it. It's not a sure thing, but like what is? Like nothing's a sure thing. But yeah, how do you get the heat? So there's a few ways to get the heat out. I think you can just pull it out of the steam. That's like the kind of dumb way. If you want really high grade heat, you actually pull it. You put other heat exchangers like in the helium line. So like if the helium's on its way to the turbine, well, you put another heat exchanger right here that grabs that heat and transfers it to maybe other helium or something else, and transfers that heat off to the industrial process. And then the rest of the heat can just keep on going to the turbine. Or you can actually have like parallel paths where like this tube goes from the reactor into the turbine, and this tube goes into the oil refinery type of thing. And so that's kind of how you would pull that off, depending on what temperature heat. And the big advantage again of high temperature reactors is that you can make high temperature heat, so you probably want to pull it straight off the helium cycle.
In terms of the temperature heat that's generated, we hear a lot about, the outlet temperature of the reactor, 750 C, some getting up maybe towards 900 degrees centigrade. And that unlocks certain industrial processes. But then, when it's gone through the heat exchanger and become steam, we're talking more sort of 500, 600 degrees C.
Yeah, that's exactly right.
That limits, still has a lot of applications, but that certainly doesn't sort of replace all kind of fossil fueled process heat.
Yeah, that's definitely true. I mean, the Japanese, we didn't talk about this reactor, the Japanese HTGR reactor has like the record 950 C for 50 days they did. So that's kind of like topping out as in terms of how high you can go with the current technology. But yeah, and the temperature you said of the steam 560 C is about right. And so, yeah, that's not amazing. So really pulling it off the helium line before it becomes steam is where it's kind of like extra interesting for the high temperature stuff.
But then you're circulating helium, and that's what's going to touch, through some kind of barrier, whatever the chemical process that you're doing.
Yeah. So maybe you bring in, and I mean, there's other, like people actually have designed things like basically like if you're doing oil refining, you can build like a heat exchanger that brings in oil and brings in helium and like does the refining directly with that heat. So like instead of a steam generator, imagine like a oil refinery stack that like just uses the heat directly. And so that's very similar to a steam generator. But instead of just bringing water in and taking steam out, you bring in oil and pull out, diesel and kerosene and butane. So like that's, you could do that without leaking helium. Like, yeah, you may not want to take helium off into some super complicated set of valves and controls and stuff. But if you could do something like that, where you just have like the use be sort of, well, at least logically close to where the helium's coming from, you can do stuff like that. So it's kind of cool. You can do like steam reforming of methane that way. But yeah, another big use is like, enhanced extraction of oil. So like that, in that case, you would use steam. In that case, they're taking the high temperature steam and shooting it underground to help push the oil out. And in that case, like, yeah, 560 C steam is fine. So I guess it kind of depends on what you're doing. If you want to like make hydrogen, that's a whole other thing. If you want to desalinate, used to be people thought, oh, we could just like go high enough temperature to just crack it thermally, but like it doesn't even make sense anymore because reverse osmosis, which is just electrically driven, is so much cheaper and easier. So it's like, okay, we don't really need the high temperature for that. Things like steel and concrete production go into like higher temperatures that you can't really reach even with a VHTR, very high temperature reactor. So in that case, you have to first make hydrogen. So sorry, this slight off ramp. In 2005, the U.S. funded something called the NGNP, the Next Generation Nuclear Plant, which is a huge HTGR government-run program. And its goal was to have an HTGR up and running by 2021. And it was based on the hydrogen economy. And so there's all this work on huge amounts of government work, $500 million at least, spent on developing the fuel and developing hydrogen technologies to make hydrogen from a nuclear reactor. And then like once you have hydrogen, okay, now you can do steel because you send that over into the direct reduction furnace and you burn the hydrogen, so you have like a hydrogen flame basically. And then you use the electricity from the reactor to do the electric arc furnace that lets you take it all the way to steel. So like
sounds great on paper.
Yeah. People have definitely thought through these processes. And there's even like General Atomic invented a process to make hydrogen at HTGR temperatures called the sulfur iodide cycle. They made that in the 70s. So, and Japan has like demonstrated it to a degree with their reactor I was talking about. So like, yeah, these things are all possible. They're kind of interesting, but they just haven't really been done at scale. So, I mean, I do think that it is justified to be working on these. Like, these are not dead ends. There's some really interesting, like making steel with low carbon nuclear heat is pretty exciting. Like, that could be very important going forward. And so, I mean, I'm very glad that people are working on this as usual. I mean, in terms of like what fraction of the total effort should be on it, like who's to say? But yeah, I really think it's like valuable to be working on the high temperature technology and these various like nuclear uses of process heat. It's one of those things where I would love to see more demos of it. Like, let's stop talking and start building. And so, and that's what people are trying to do now. So I'm fairly happy with what we're seeing, but yeah, we just have to follow through on some of them.
So, in terms of, I guess the challenges, we talked about, sorry about the dings, everybody. We talked about, in the early days, Rickover walking in and maybe it was Weinberg as well, or maybe it was Weinberg's reanalysis. Can't remember. It's only been an hour ago, of the fuel cost. And that's quite significant with the need for HALEU manufactured into TRISO, particularly at current costs. We had Cruz Shervan on, and he was saying, listen, the advantage of nuclear is that the fuel is really cheap. Fossil plants, low capital cost, but high operating costs driven by fuel costs. And if nuclear can't live up to its cheap fuel, that's a major issue. And it doesn't seem like there's any way around using, medium enriched uranium, as we like to call it, because of the shitty neutronics, and TRISO because we need a fuel that doesn't melt. So that seems to be a challenge that's potentially solvable, but a major challenge.
Yeah, it's a big challenge. I mean, the gas cooled fast reactors don't use TRISO fuel, but I don't even know how they plan on doing decay heat removal. So that's a whole other story because they want a lot of those fast reactors are running at 10 times the power density of a typical HTGR. So they must have active safety systems. So leaving that aside, yeah, I mean, the fuel cost thing, in terms of, I think this idea of adding thorium and doing breeding to extend the fuel resources, that makes it so you're not, even though you're using higher concentrated fissile, you could imagine a world at scale where, because you're breeding, you could not be using too much of the world's uranium resources, even at large scale. So that does offer a path. Not too many people are talking about thorium breeding in HTGRs right now. It's just another complication. You have to have extra processes, a whole reprocessing step, more cost and everything. So, at least that could hit the uranium, the SWUs and the uranium mining cost. And then it all comes down to what can you do for TRISO fabrication cost? And yeah, it's high, as Karush was saying. People are working on it. There are challenges to scaling it. You can modularize it to a degree, but you still have to worry about criticality. Some of the like processes for making TRISO only works at like a certain batch size, or else you get too many, particles that are out of spec and stuff like that. But and this is something that before they folded, UltraSafe was like really working hard on designing like the most economical possible TRISO fabrication facility, and that was bought up by someone called Standard Nuclear. And so will that continue? Other people are trying to make TRISO, Waxman you had on earlier for the Project Pele. They made they're making TRISO fuel right now down in Lynchburg for the Project Pele. And how are they doing on the cost? And then what's it looking like? And how's Kairos and X Energy, how are they doing on cost? Like a lot of these things we don't really know. They haven't published like what the current costs of fabrication are and what the trends are. And then what about China? Like China just building 12 of these huge ones immediately after running their demos. And so, I mean, they're making TRISO fuel somewhere in China. And my guess is like when they look at it, they're like, yep, it's looking good. Like it's looking reasonable enough to put in these 12 packs. And so that, I mean, there's probably some reason to think it's not going to be a blowout. And maybe it can be reduced farther. I don't really know where it'll end up. It's still like a pretty boutique process. Like probably in any case, it'll probably be hard to get as good as doing like uranium oxide fuel. But I don't know. This thing from China kind of shocked me when I saw the pictures of those 12 packs. I was like, damn, they're really going for it. And maybe they just want to do it at scale, and it's still it's still more expensive. That's certainly possible. But I don't know. At least they certainly think it's interesting.
Yeah, definitely. I mean, they don't have the benefit of fracked ultra cheap natural gas as well also, to compete against. So that helps. We're going to wrap up any minute. I promise you. I guess the other question is scaling. So you mentioned these reactors have to be quite small. Certainly Peach Bottom uneconomic because it was so small. That sounds like a challenge, but maybe one that can be met as the Chinese are doing with modularity, with multiple modules sharing INC, sharing a whole bunch of shared infrastructure, maybe a turbine or a containment building. So that sounds solvable, but a challenge.
It's another shot. Like people tried 300 megawatts. Now we're trying 100 megawatts, and we'll see where it ends up. And will it, yeah, we'll have to find out. In 10 years, we'll see how many HTR 600s China's building compared to how many whatever else they're building. They just turned on that molten salt reactor as well. I mean, the little experimental one. And obviously, there are dozens of light water reactors under construction. So, yeah, it's very hard to say. Certainly, the next shot is this 100 megawatt scale that pretty much, a lot of people are doing. We talked about them a lot on the microreactor episode, but there's a bunch of tiny microreactor companies using the same basic technology, helium, TRISO, with HALEU. So that's a small size, but most of them are targeting like fringe markets where you're willing to pay 10 or 20 times more for the ability to be like remote and mobile and stuff. So that's like Pele and all those guys.
Okay, I mean, I guess my final reflection is just how things have changed so dramatically in the U.S.-China relationship, where there was a lot of collaboration on the AP1000 build, certainly early on. The idea that relations were so good that we could learn a lot of lessons learned from Chinese work on those AP1000s, and just how that relationship has deteriorated so dramatically, such that we're not able to benefit and share some of the learnings from reactor technologies which originated in the U.S. and are getting kind of perfected in China. It's just from kumbaya, let's solve climate change, let's all work together on some big common shared goal. It's a real tragedy, the situation we're in, where the world's kind of epicenter of nuclear construction activity and R&D is behind the new Iron Curtain.
Yeah, as I'm very disappointed by this. And I was going to make a tweet about this. People talk about like, oh, we better make reactors now because we might fall behind China. But like, you look at what China's doing, like we're way behind. We're 20 years behind. And so, and it's like blatantly obvious when you look at what they're operating, the different types of reactors. So, and yeah, it's a great shame. They openly admitted for the molten salt reactor, like, yeah, we just read all the Oak Ridge documents and went off and learned all. And so like now, great, they are picking up where Oak Ridge left off, and they're building on the technology. And like, how beautiful would it be if we could then sort of relearn from them all those lessons. But right now with the relationship, it's basically like closed off. It took like a year for me to find out that the thing even was critical. I probably could have known earlier, but it just isn't being discussed as publicly at this point. And we just aren't interested in like saying like, hey, how's your OpEx on that molten salt reactor? How's that HTR looking? Like, what lessons have you learned? Like, that forum would be extremely valuable. And yes, I totally agree. It's a great shame that we don't have that right now.
Okay, Nick, we got to leave it somewhere. Still, so many more little bits of esoteric we could have dived into, but I think that's all we got today, and certainly demystifies a lot for me. And I think one of my big takeaways is that again, I think in terms of Gen 4 technologies, HTGRs seem to be probably at the highest technology readiness level. I'm not sure if you'd agree with this, but probably even ahead of sodium cooled reactors. We have the BN series operating in Russia, but we have. Would you say it's a tie, or
my gut is that it's like it's a tie. I mean, yes, all the CO2 ones are give them an advantage, but like from helium perspective, I'd say it's closer to a tie. But I'll have to look at it. You may be right. Like I believe that HTGRs have a little bit more OpEx on them, but it's close. I think they're like very similar.
Okay, Nick, thanks again for making the time. Today's episode was made possible through a generous donation from the Xerxes Foundation and from listeners like you making pledges on our Substack. If you'd like to join the tribe, please do head over to our Substack, smash that pledge button, or if you would like a tax-deductible receipt, you can hit the donate button and make a contribution through our fiscal sponsor. We genuinely appreciate your support. It is only through your generosity that we are able to continue to offer energy literacy on demand.